Welcome to Talk Universe. This is our show for Wednesday, November 30th, 2016. Tonight's subject is one that touches us all: clean water everywhere. Let's talk about water, its source, what it does, how it acts, and how important it is. We'll also look at how we can ensure a permanent supply of clean water everywhere where we need it. We know that there is water everywhere in the universe, and the Earth has plenty of water as well. We can look to the outer planets and see huge seas of ice and some interior oceans of liquid water. Water is one of the most common molecules in the universe, and it's a very simple molecule. It's formed in nature all the time. We have a limited supply on Earth, and yet within those limits we have oceans and oceans of water that we will never see. Much of it is trapped inside the rocks of the Earth in the mantle, well beneath the crust. If we look at the Earth from space, we can see that almost 3/4 of its surface is covered with water, and yet this isn't drinkable water for the most part. It's salt water known as brine. Our oceans are full of salty water. Water has some fascinating properties. First of all, as mentioned, it is a simple molecule. It consists only of 2 hydrogen atoms and 1 oxygen atom. This combination yields a molecule that is a solvent, has interesting physical properties and a wide range of heat-carrying capacity, and is also necessary for the formation and sustenance of life as we know it. When you lower the temperature of a material, generally it shrinks. Water is unusual in the fact that it freezes and expands, so making it colder actually makes it larger in volume. It's one of only a handful of substances that actually does this. This is why ice floats in water. It actually has more volume or less density than the liquid water. This also makes water a powerful force for erosion. Water soaking into stone or filling voids and then freezing can expand enough to fracture the stone and break it down into gravel and sand. And running water in streams can actually tumble and erode stones until they're smooth, and can even sort them into large, medium, and small grades based on how rapidly the water is moving. We find huge banks of gravel, all basically the same size, due to the sorting effect of moving water. On the Earth, we find water in all 3 of its different states: solid, liquid, and gas. This is also true on Mars. However, on the outer planets, water exists basically as a mineral. You see, under the conditions that the water is found, it usually is an ice and frozen very, very hard. Under those conditions, the water actually can be broken down and eroded, fractured, and tumbled, just as any other mineral or stone might. But sometimes we find pockets of liquid water deep inside these places, particularly the moons of larger planets such as Jupiter and Saturn. In these cases, water can actually erupt from volcanoes, cryovolcanism, so that the liquid water is the lava and it freezes into hard water stone. This may seem unusual to us, but the universe is a big place and many different sets of conditions exist that we as humans normally won't encounter. Cryovolcanism is just one of those conditions. But where does water actually come from? There are numerous sources, but the most common one is space itself. You see, hydrogen is the most abundant substance in the universe, and it exists everywhere in space. Even the vacuum of space isn't entirely a vacuum. There is a thin hydrogen gas spread throughout all of space right now. This is where the material to form new stars comes from. But whenever a star burns out, it usually explodes and throws a lot of material into space, and some of that can be oxygen atoms. When these oxygen atoms encounter the hydrogen floating in space, they can combine to create hydroxyl ions or water molecules. And water does exist in huge clouds spread all throughout space, and we can detect that by optical or radio methods. In fact, water has colors, but we can't easily see them with the human eye because those colors appear transparent to us or invisible. Water absorbs infrared very strongly, and it even absorbs red light 100 times more readily than it does blue light. Infrared light is absorbed about 1,000 times more easily than ultraviolet or violet light. So if we could take pictures of water across the spectrum with different filters, and we could compare them, we could see that it was absorbing the infrared very strongly, and that would be one of the clues that what we were seeing was in fact water. But mostly when we look for water in space, we use radio telescopes, and they give us a very clear picture of what's present. Water, when ionized, can give off distinct radio waves that are very easy to detect. And this is one of the methods we use to see water very deep in space. Large molecular clouds can be found that contain water, ammonia, methane, alcohols, and other molecules very easily this way. Each molecule has a specific fingerprint. Water is no exception. So we can see that the hydrogen in space and the oxygen from exploding stars, novas or supernovas, form water everywhere. And we also see that it is extremely abundant in our solar system. We can tell that water is one of the most common molecules in the universe. But how does the water get onto a planet such as the Earth? Where did all the water in our oceans come from? When we look at other planets, we often don't see a lot of water. For instance, Mercury is bone dry and has a vacuum instead of an atmosphere. Venus is extremely hot, and we certainly don't see water there. Earth is the most clement planet in our solar system, and it has plenty of water on its surface. That might be actually one of the reasons that defines it as being a clement planet. The conditions are right for the existence of liquid water in abundance. After all, even if the temperatures were comfortable and the air pressure was reasonable, if there was no liquid water present, then life probably wouldn't exist there, and it wouldn't be clement after all. But water also plays an extremely crucial role in the formation of planets, particularly terrestrial planets. And this is something that most geophysicists have not thought about. When planets form, they don't do so simply under the influence of gravity, but also due to the presence of water, or ice more correctly. Planets form from rock and dust and other materials in a stellar nebula or a protoplanetary nebula. This is a large dark cloud of gas and molecules that exists in space. Under the influence of gravity, these materials do come together, but other forces take place as well. You see, tiny particles of dust and mineral in space will not stick together when they collide. Usually they'll bounce apart. Something has to hold them together, and these particles are far too small for anything like gravity to exist in any reasonable quantity. Electrostatic force might do it, but what would be the source of it? In fact, it takes particles that are coated with a thin layer of water ice sticking together to grow properly to form larger and larger chunks. This is a crucial part of the issue about the sources of the oceans and atmosphere on terrestrial planets, and something that most scientists haven't yet considered fully. Water ice has an interesting property, and it is this. If it is impacted, at the point of impact it liquefies momentarily, but as soon as the force of the impact is removed, the water freezes again. This process is called regelation, and it's something that's easy to demonstrate if you had a block of ice, a brass wire, and two heavy weights. If you string the brass wire across the block of ice with a weight on either end, the weights will pull the wire into the ice, and slowly the wire will penetrate the ice, slide all the way through it, and end up at the bottom. Common sense would say that the wire had sliced the ice in half, but in fact the block will still be solid. The wire moves through the ice without actually melting it. The effect can be demonstrated very easily if you had two small snowballs. If you hang the snowballs from strings and allow them to bounce off of each other lightly, at just the right collision speed, they will stick, because the ice at the point of contact will have melted and then regelation will occur. This is the process that makes the particles that form planets grow larger and larger. That thin coating of ice allows them to stick together. Even though this process is easy to demonstrate and understand, a lot of people miss the implication that planets automatically have some fraction of water included within their makeup at the time that they are forming. This water also has another interesting property. It has the ability to absorb other materials from the stellar nebula, such as ammonia and methane. Many molecules will stick together with water without actually chemically bonding to it. We've all heard of methane clathrates on the ocean floor and how warming them can contribute to global heating. This same process is what binds these molecules into the bulk of the material that makes up new planets when they're in formation. So the water not only helps planets form, bringing them together and sticking the pieces together, but it also participates in adding gases that normally would be volatile or blown away from dry rocky material or metals. These materials, when combined, are inside the magma, the molten material of a planet, as it gets hotter and hotter. And the chemistry that occurs inside the magma, using water, ammonia, methane, and other molecules, is what produces our water, our atmosphere, and our petroleum. So there's a simple pathway from the dust and gas that planets are formed from, and the genesis of oceans and air. Now, scientists are still puzzled today about how so much water reached the Earth, and many theorize that it was brought to the Earth by collisions with comets or perhaps asteroids. In fact, this isn't even necessary. There's proof that the water on the Earth is not water from space, but from some other source. This is because water on Earth has a specific composition that doesn't match the composition of water found in comets or asteroids or seen in space near the Earth. What's different is called isotopes. Let's suppose you have oxygen. Oxygen is element number 8 and has an atomic mass of 16. But some oxygen has more neutrons and is more massive. Oxygen 18 is found in water from space, but rarely in water on Earth. And in the same vein, hydrogen in space can also be heavy hydrogen, such as deuterium, or normal hydrogen, which is known as protium. When we look at the water from space, we see that the oxygen-18 ratio and the deuterium ratio is very different from the ratio of the water found on the Earth. This means they couldn't possibly have the same sources. Something different has happened, and comets couldn't have brought it to the Earth. As it turns out, molecules trapped in the magma inside the Earth are subject to chemistry. Ammonia, methane, hydrogen, and other materials that were trapped by the water molecules in the beginning now react with the other materials inside the Earth, such as the minerals and oxides. This produces water as a byproduct and also produces the nitrogen in the atmosphere from breaking down the ammonia. Now, a clever theory is great, but in science we need some sort of evidence or proof, and we do have that. By scanning seismic waves that move through the Earth, large pockets of water have been located deep within the mantle, some thousands of miles underground. In fact, more water has been found inside the minerals of the mantle of the Earth than in all of the oceans of the world combined. This means that there is a huge reservoir of water underground, and it probably got there at the formation of the planet through chemistry. It turns out that the minerals that the mantle is made of, mostly perovskite, actually are very good at absorbing and trapping water. They also have the ability to act as a sieve, so the water can pass through them slowly or be stored in those molecules in the rock. So a small quantity of water is necessary for the formation of planets, but once this process occurs, water is being generated inside those planets to form enough material to make oceans, many oceans worth of water. This is what happens on probably every terrestrial planet throughout the universe, and the implications are that water should be present in many worlds. Over time, that water would be exhausted through volcanic eruptions, which produce up to 80 to 90% water vapor as steam, and it would also leak up through the ground through water tables. So water can be formed in the ground and come up to the surface slowly over geological periods of time, filling the oceans, filling the atmosphere, and creating the environment that harbors life. Primitive oceans on a newly formed planet would probably be full of sulfate minerals and sulfate salts, and this is for a very simple reason. The presence of oxygen changes the pH of the water in the oceans, and this makes many minerals precipitate out, such as gypsum. Over time, the activities of life itself changes the chemical composition of the oceans. Eventually, the sulfate minerals disappear or end up in springs or in mineral deposits, and chlorides begin to dominate the ocean chemistry, such as sodium chloride in our own ocean. So this explains the generation of water and atmosphere on the Earth and most any terrestrial planet, and it tells us where the oceans came from and why they're salty. Water flowing through rock substrates will dissolve salts and carry them to the surface, but fresh water is another issue altogether. That happens because of evaporation, something called the transpiration or water cycle. Any open body of water, such as a lake or an ocean or a stream, or even the soil itself with moisture in it, contributes to evaporation. This water is actually pure water, because salt doesn't evaporate, nor do minerals. So this water ends up in the clouds, in the atmosphere, rains back to the ground. And over many cycles, it washes the soil, it washes the salts, and brings them down to the oceans. So the water is concentrating the salts in one location, the seas. Over time, the rainwater percolates back down through the soil and finds itself in reservoirs underground, porous rock that can hold the water and filter it. So the rock actually filters and stores the water for us, and this is the origin of the water table, in part at least. Rainwater can dissolve carbon dioxide, forming a weak acid known as carbonic acid, and flowing through these minerals underground, combined with the action of bacteria that consume minerals, we see the formation of caverns and underground rivers larger than any sort of water or estuary or river system we see on the surface of the planet, all beneath our feet and invisible to our eyes. After the break, we'll talk about the largest reservoirs of fresh water on the planet and how they got there, and the threats to our existing water system on planet Earth today. Are humans and our activities threatening the supply of fresh water on our planet? This is Talk Universe. In the Earth's earliest history, the atmosphere was incredibly dense, 250 to 300 times what we see today. That has a lot of effects. It also was likely over 400 degrees centigrade, perhaps as high as 450. What this means is that water as we know it couldn't exist at all. It was neither a liquid nor a vapor, but something in between called a supercritical solvent. This is a state that's a borderline between a liquid and a gas, and it has interesting properties because water in this form can dissolve many materials that normally it couldn't. But you see, the atmosphere was thick with volcanic exhaust because the planet was literally a ball of lava. Under these conditions, steam venting into the atmosphere would remain in that suspension. All the material, all the organic molecules formed, all the materials that water can carry as a solvent would end up sitting in this stew, this amazing steam house of an atmosphere. In this place, we would expect that the first organic chemistry took place. But aside from that, there's another interesting thing that would happen. As the pressure dropped and the temperature dropped, a specific point would be reached where this supercritical state can no longer be supported and the water would have suddenly reached a liquid phase. At this point, all the mud, gravel, and material supported would also be released, and we would see a thundering deluge of mud, organic material, and ocean unlike anything the world has seen since. It would be capable of slicing channels and gullies and valleys in no time. It also wouldn't be unreasonable to think that these flows would be at least half a mile in depth. So we can think of billions of tons of muddy, sluicing material cutting through the hot, steaming environment of the Earth billions of years ago, not long after it formed, and this being the beginnings of life and the formation of the oceans. But how did this lead to the formation of fresh water that we have on the Earth and the aquifers that we have today? Actually, it's not that difficult to see. Once the process started, evaporation would have taken over, and water would have left the oceans, reached the skies, and carried material back to the ground. This cycle didn't just clean the soil of salts and other materials, but it also would have cleaned a lot of material out of the sky itself. Think about today when you see a rainfall leave pollen patterns on the windshield of your car. The raindrops are actually capturing the pollen as they fall and depositing them on the ground or on your windows. So we can see a process developing. Water as a solvent can carry materials from the sky and from the land down to the ocean, thus cleaning both of them. Materials removed from the sky can sometimes end up in the land and often end up in the seas. Salts and other materials that can be dissolved on the soil can be carried down to the ocean. Eventually, this process leads to both the sky and the land being rather clean. Now, we can begin the process of generating clean water. In the beginning, the water that does land on the soil can penetrate the soil and eventually generate underground reservoirs, as mentioned previously. This material, the stone itself, acts as a filter and can remove some impurities from the water after it's been washed a number of times through this process. In the skies, materials such as dust and airborne particles, such as salt from sea spray, end up being washed out as well. With clean air and clean soil as a template, the clean water can begin to accumulate and establish flows. Streams and rivers are generated, and at high altitudes where it's possible, snowfall can develop. Packs of snow and ice at the peaks can now provide the function of generating a constant or at least fairly constant flow of clean water that's available perhaps year-round. And at polar caps, when they're cold enough to form, ice will begin to accumulate. This ice is generally very clean water, and we can look at the ice that's generated in times past and find records of fine particles that are caught in it, such as diatoms, tiny bits of minerals and dust from storms over deserts and arid areas, and pollen grains or tiny spores from things that might have lived on the land at the time. One interesting factor is that frozen water, ice, actually acts as sort of a time delay, so that as it's released slowly, when it does melt, you have a stream of clean water that's available for organisms that need it. So this gives us a pretty good idea of how nature cleans the air and the soil and carries the material to a distant location, the oceans, and how the water itself becomes clean in the process. Being a solvent, once it evaporates, it leaves behind the load it was carrying and becomes purified. This distillation process is natural and is the basis of all rainfall on Earth. But the process of generating clean water in times past can be interfered with in a very bad way. In the past, materials generated by nature or any sort of natural event generally would be carried to the oceans where they would be either fixed, consumed, or transformed by organisms or natural processes. This isn't always true for things generated by industry. This is one of the problems that we're facing today. Chemicals generated by industrial processes, agricultural processes, fertilizers and pesticides, and medical processes such as drugs and hormones can have terrible effects on the environment, and no organisms exist to naturally break them down in many cases. While it's true that nature can destroy this material over time, it doesn't mean it's going to happen in a timely manner. Some of the things can last for hundreds or thousands of years, and in the process of being broken down, many of these compounds are used by organisms in ways that were never intended. Some of them act as regulators or interfere with the natural growth or reproduction processes of living organisms. Many drugs used today are either created by modifying organisms to produce them or by advanced biochemistry. Many of these molecules don't exist in nature, and organisms in the wild don't have any way of distinguishing them from their normal hormones or growth factors inside their bodies. As a result, their life cycles can be disrupted, growth patterns and even gender can be altered. Many times we only think of larger organisms when these sorts of problems crop up, but we never really consider what happens at the very basis of the biological chain. We know that it takes tiny organisms, and many trillions of them, to support the life that is larger. A great case in point is those diatoms in the ocean, zooplankton, phytoplankton. Basic organisms gather the minerals and the energy of the sun and convert it to all the food that the larger creatures eat. When these smaller organisms are affected, it can have disastrous consequences all the way up the food chain. And some toxins are so potent that a single molecule can kill a cell. A case in point is ricin, the compound that is derived from the castor bean. Now, as mentioned previously, we normally wouldn't worry about toxins being carried into the ocean, for instance, and the rainwater emerging fresh. But the fact is, most of the life on Earth that we see that has an effect on our environment is in the ocean. And this means that toxins carried there that are not broken down by normal biological processes can persist and have long-term effects. But in many cases today, drugs are ending up in our aquifers because of how we treat our wastewater. This material never reaches the ocean in many cases. Instead, it ends up in our wells and on our drinking supply right on the land. The other issue is that there are numerous types of contamination. Some are natural elements that are poisonous in their own state, toxic materials such as hexavalent chromium or arsenic. Other materials are poisonous because they carry some action on a biological level, molecules that are typically very complex, organic molecules. In this case, they basically can be broken into two categories: those which heating can destroy, which are protein-based, and those which cannot be destroyed by heating. On the other hand, we also have organisms which can be carried in the water, which can be very dangerous as well. We can basically classify the contaminants as 6 different categories. Number 1 is particulate matter. Number 2 would be perhaps organisms. Number 3 could be metal and inorganic poisons. Number 4 could be salts and minerals. And number 5 could be organic toxins, with number 6 left for radiation or radioactive materials. Each of them has a different way of being dealt with. Particulate matter is the simplest, the first one. Particulate matter can be filtered out with something as simple as a sand bed filter. In many cases that works quite well. Organisms are a little more difficult. They can cause infections or illness, or they can make toxins as well. Some can be filtered, but for the most part they have to be boiled or chlorination has to be used. Ozone often works very well in this case. The metal and inorganic poisons, for the most part, distillation is the way to go. That's the only way to get some of those things out. For salts and minerals, reverse osmosis can work quite well, and it isn't as energy expensive as distillation, but you can distill it and that's the end of the problem. Organic toxins can be removed sometimes by something as simple as charcoal. Normally you would distill water for this, but sometimes ozone can break down the organic molecules well enough to make it safe to drink. Radioactive materials are another thing. It really depends on the type of radiation. Some radioactive materials can actually be part of the water itself if the oxygen or the hydrogen are radioactive isotopes. That can't be removed. You simply can't use this water, and it's very difficult sometimes to sort it out from other water that's drinkable. Radioactive materials, for the most part, require distillation, but if it's the water itself that's radioactive, there's nothing you can do about that except to wait. For most water purification, we can use methods we learned from nature. Sunlight causes distillation to occur. The water evaporates and leaves whatever it was carrying behind. This is a very effective method, but it's energy intensive. Filtering is also very good at removing particulate matter. That's the stuff that's hard pieces like grit or sticks or materials that contaminate the water in a physical sense. This isn't generally toxic material, but it's simply plain unpleasant to have in your water. Some chemical or organic matter can be removed with something as simple as a charcoal filter. Activated charcoal has a great deal of surface area, and it captures particles and allows the water to flow through it. In most cases, if you simply filter the water through a sand bed, chlorinate it or boil it, and then run it through a charcoal filter, you'll have perfectly drinkable water. These 3 steps will work for 90% of the contaminants that you're likely to encounter. And while distillation is usually 100% effective for almost everything except specific types of solvents, it leaves the water flat and tasteless because it removes all the minerals as well. Most systems that depend on generating distilled water have a remineralizer used to put minerals back in the water to reduce its aggressive solvent properties and improve its taste. In nature, this happens because most of the rainwater is filtered through a system such as soil or minerals or rock. This puts the minerals back in the water that normally we expect to have. And there are some pretty innovative technologies for getting drinking water in places where little or no water is available. One is called air-to-water. Anyone has noticed when they run the air conditioner in their car or in their home, there's usually a great deal of water, moisture generated because of condensation on the cooling coils. This is actually distilled water from the atmosphere, but normally it isn't suitable to drink because it's on the outside of a piece of aluminum that may have any sort of contamination on it. But in an air-to-water machine, they actually use a stainless steel or similar material that won't contaminate the water. This is chilled and condensate forms on it, which is then filtered, treated with ultraviolet light to destroy any organisms that might be in it, and then it's remineralized. A cartridge of minerals containing silicon and other material is used to pass the water through and improve its taste. But the issue with air-to-water technology is it's very energy intensive. Now, while it will work just about anywhere, it usually is reserved for generating drinking water because of the small quantities and high expense of it. However, it can be used in areas where there's a great deal of humidity if energy is plentiful, and then it can be used for agriculture and other purposes as well. The real test for the efficiency of a water system is its ability to generate drinking water from seawater. For this purpose, there are 3 technologies that tend to dominate the field. The first is reverse osmosis. This is a system that actually allows the salt molecules to be separated out. And realize salt doesn't really form molecules when it's in solution, so it's a tricky process. It uses a specialized porous membrane. The second is distillation, and because of the high cost of energy to get the water up to boiling, it usually uses a few tricks such as partial vacuum to lower the boiling point or compressed steam to recover the heat and put it back into the system for a second go-round. The third is solar troughs, where you literally have a long, thin trough of seawater evaporated and captured in a secondary trough that is cooled slightly, even by the environment. But the cost in the solar evaporative trough method is in land area and lots of material. It can be done with simple materials such as thin plastic used to make greenhouses. But the problem is then the plastic breaks down over time and this becomes another expense. But it also takes a lot of land, and in areas where land is at a premium, it doesn't really work very well. In coastal areas, it's possible to put up windmill-driven towers that pump seawater up to a high altitude and then spray it through a fine nozzle after heating it slightly. What this does is it increases the amount of moisture in the air, and as the water evaporates, the salt crystals come out and drop down to the sea surface. So this can increase the amount of humidity locally and drive up the amount of rainfall in a very natural process. The issues in this case center on aesthetics. When it was proposed that a wind power system would be placed offshore, just over the horizon, so that people could get power fairly cheaply in one of the areas of Massachusetts, the people were outraged. The thought of these windmills spoiling their view was more than they could take. And yet at some point we have to make a concession. If we really want clean water and cheap power, we have to do something about it. Where it's feasible, there have actually been plans for retrieving icebergs, bringing them back to port, and carving them up and using them as a source of water. They would take very minimal processing to be usable as drinking water in many cases. But the cost of fuel, shipping, and liabilities all turn into big issues in a very short order. And another factor is most of the water we use is actually for agriculture, not human consumption. If we had a way of getting our water supply to the point where we could get cheap, easily available water for agriculture and livestock, we'd be way ahead of the game. Of course, we do consume a lot of water for cooling power plants, but that's another issue. Using alternative power systems can actually reduce this by a factor of 6. The average U.S. home uses about a cubic meter of water per day, yet the power delivered to that home requires 5 cubic meters of cooling water. This is Talk Universe. When we look at the amount of water available on the Earth, it's hard to realize that the water in the oceans is not usable for agriculture or drinking, and yet it outweighs or outmasses the clean water in the world thousands and thousands of times over. There's a very small amount of actually clean, fresh water on the Earth. Most of it is tied up in things like Great Lakes and ice caps. Making fresh water comes down to energy, and nature has a lot of that in abundance. And yet we're not very good at generating it without burning something. We have the ability to generate a lot of power from wind and sun and the movement of the ocean, and yet we don't seem to use very much of it. However, all the clean water in the world was created through natural means. But while nature was generating a lot of clean water, we've become very adept at tapping into and emptying the aquifers and not replacing what we've used. This is basically the source of our crisis. We're contaminating the water that there is and we're using it up without replacement. It really comes down to two issues. The first is uncontrolled growth, and the second is poor management of the resources that we have. We don't seem to be very good at putting things back once we've taken them down and played with them. Furthermore, we often place things in an area that they shouldn't be in. For instance, running an oil pipeline underneath a major water artery. All it takes is one fracture in that line or one leak, and the drinking water for millions of people will be contaminated. And yet we do this and allow it constantly. Fracking is a case in point. There are natural barriers between the oil and petroleum reserves underground and the water supplies that we drink. These are the things that we depend on for our livelihood. And yet, we're allowing companies to put explosives underground with solvents and to detonate them and fracture the stone in hopes that they can wash out some small vestige of oil. What happens is the fracking chemicals that they use leak into the water table and end up in people's drinking water. The interesting thing is that many of these things are solvents and detergents and other materials that are actually carcinogenic or flammable, and yet you're not allowed by law to find out what's in the water when it's contaminated. You see, the companies that do fracking have found a way to legally challenge anyone by claiming intellectual property rights. If you analyze the contents of their fracking fluid, then you can go to jail. For some reason, it has been decided in a court of law that the importance of the secrecy of their chemical formula is greater than the need to protect the water supply that keeps us alive. How this could even be debated in the first place is a true mystery. None of it makes sense when you really confront the issues. At the present time, there are even studies going on to see if wastewater from oil fracking can actually be used to irrigate crops successfully without damaging them. The crops may survive or they may not, but the best solution is not having to irrigate with oil production wastewater in the very first place. After all, even if the crops grow successfully and don't prove to be toxic or harmful, what's it doing to the soil and the bacteria that live there to produce the things necessary to grow crops? You see, soil isn't just some ground-up sand or rock. It actually is a living culture of organisms that make the minerals available for the plants to consume. Another issue is that many times water sources are restricted or controlled by local governments. A perfect example is injunctions against collecting rainwater for use to water your property or your plants. This makes no sense at all. Even if you collect rainwater, it doesn't simply vanish. It actually is returned to the soil and makes its way through the system again. So collecting rainwater has virtually no effect whatsoever on the water that's circulating in the rivers and waterways. It can be successfully argued that collecting rainwater actually slows the loss of water or passage of the water through the system, thus increasing the reservoir that's on hand. And rainwater cisterns mean that community plumbing projects can be much smaller, have a smaller impact on the environment, and much easier to manage. This can result in fewer wells being drilled and less chlorine being injected in systems that are built. By using alternative energy systems and having your own rainwater collection and purification, you actually make a much smaller impact on the environment, and you also end up with systems that are easily repaired or replaced if necessary. This isn't true with the utility system or an electrical grid. They can be extremely difficult to replace and mean huge expenditures of time, effort, and labor must be made. A perfect example was made clear with the Flint, Michigan water crisis. It's not going to be possible to replace all the pipes underground that have been contaminated as a result of this issue. And a lot of it has to do with the sort of sterilization systems used to make water drinkable. In many cases, chlorine was the de facto standard for many, many decades, and as a result, the pipes became, in a sense, conditioned to the chlorine. When they changed in some areas to other systems, such as peroxide or ozone, what would happen is it would break free chemicals that were deposited on the insides of the pipes and laying there benignly. Now with the new sterilization system, chemical reactions occurred and the water became contaminated through reaction with the interiors of the pipes. This is another case where it's almost impossible to fix the system without ripping up all the pipes previously buried in the ground. It means, in many cases, a complete rebuild of a water utility system. For small independent systems, this would never be a problem. If you had an issue, you would know right away with a water test kit. You could immediately flush your plumbing out or replace it in a couple of days, and everything would be fine. Covering all these issues is of course essential so we have a broader understanding of the issues involved and some of the problems that you're going to encounter if you're trying to provide municipal water for a city. But what really stands out is our need to come up with methods of generating a lot of fresh water very cheaply and easily. And it seems to me that the best systems would be a combination or a hybrid of biological methods such as bioremediation and high-tech methods driven by alternative energy systems. There's presently a great deal of public land which would be commissioned easily into producing systems that would make biological filtration for water systems, and then turn that water around into a high-tech filtering system such as a reverse osmosis or steam sterilizer, and then produce the drinking water we need in quantity. And it should be based on not only the water that is available in an area without tapping into a major aquifer, but also on rainwater collection. We need to make systems that act as biology, as nature does it, and then expand on them with what we know. In virtually every water system we have presently, we discharge the water back into the environment, because really we're taking water from the environment at the input end. So the process depends on the natural cycle to get the water into the system and carry the water away when we're done with it. But the problem is we often put things in the water that don't easily get removed by natural processes. We also don't have man-made aquifers that we can store that water in most cases in times of drought or need. Now in a really worthwhile system, we'd have the ability to store that water somewhere in the interim in a clean form, and then we'd simply clean and reuse the water that we have on a constant basis. One of our major issues is the fact that we have no means of controlling the growth of users. When people move from one city or one state to another, we end up with more users on one system and less on the other. Add to this constant growth and the fact that there's very little we can predict except through statistics. We don't really know for certain sometimes just how much excess capacity we need. But if we were to plan in advance and say, overburden it by 30%, then we would probably be in the ballpark for almost any situation we would encounter. In the best of worlds, every community would probably create as much drinking water and industrial water as it needs, and it would always be replaced. And then whenever weather made it available, they'd have something to work with to build up their reservoirs. But when it comes to planning and executing these things, we find that a lot of money vanishes, a lot of meetings are had, and a lot of paperwork is generated, but nothing really changes in the end. This is something that has to be dealt with. A perfect example of this is the global warming issue. No governments appear to be doing anything to curb warming other than putting restrictions on industries, and yet if they simply planted trees, that would solve almost all of the issue up front. When you add to that the fact that almost all of this is controlled by economics, the flow of money, rather than what we need, then it's easy to see the controlling factors don't have the interest of the people in the community in mind. Cities in general have to be designed according to a template that works well in accordance with the laws of physics and economics. Physics is always going to win, no matter how many dollars you have, however. Another idea that was proposed many decades ago and really makes sense today is the possibility of a huge water management system that actually moves flood waters to drought areas. It could control the flow of water during times of weather extremes and help manage water during normal periods of time as well. The system could easily be built without destroying the environment by placing it mostly underground and powering it with environmentally friendly energy systems such as windmills and solar panels. Something else that would be a great help to cleaning up the world's water contamination at this point would be to curb the use of prescription drugs on such a widespread basis. There are literally tens of millions of people on prescriptions in the United States on a daily basis, and this means that whatever they take ends up in their urine and then in the wastewater stream. Even now it's shown that our water from the city utilities is laced with all sorts of drugs and psychoactive compounds, including stimulants and depressants and hormones. This can't go on. This sort of low-level exposure can have unintended consequences, and it's certainly possible that it could be at the root of many of the maladies we're suffering today. As a result, whatever system we put in place to generate clean drinking water and clean industrial water has to be capable of eradicating these compounds. One novel solution for increasing the amount of humidity in the atmosphere and controlling the weather, basically rainfall, is to put large solar power satellites in orbit that generate a low-level beam of microwave energy that could heat the ocean layers and create enough transpiration, evaporation driven by microwaves, to actually increase the rainfall in a given area. One of the side benefits of this system is it would have the ability to steer hurricanes away from land and reduce their effects on our homes and cities. But the big issue is how much energy it takes to convert water into a vapor. It takes an immense amount of power to do it. When you look at how much energy it takes to melt ice versus boiling water, you'll find that the heat capacity of water is an amazing thing. It's one of the reasons we use it for steam power the way we do and depend on it so much in an industrial sense. The amount of energy necessary to melt 1 gram of ice from 0 degrees C as a solid to 0 degrees C as a liquid is the same amount of energy it takes to raise that same gram of water from a temperature of 0 degrees C to 80 degrees C. It's an incredible amount of energy. This helps us understand why it takes so much money to make distilled water. The amount of energy required is the real showstopper. But there are some clever methods of using heat exchangers to recapture the heat in the steam and then reuse it to warm the incoming water. And the incoming cold water can be used to condense the steam, thereby supplying the cold. So there are some tricks we can do that help us save some energy. But nature has the advantage of an entire star and an entire planet, and the energy from it to be used in the process of creating clean water. We have to be a little more clever. We have limits to just how much engineering we can do without wrecking our environment, even though we seem to be doing that right now quite effectively. We could use orbital microwave systems to provide the power, or we could use public land that is repurposed specifically to recycle water properly. If we were to create basic wastewater recycling systems that were closed cycle, then we would have the answer, and it wouldn't take a whole lot of engineering to do it. And the factors are pretty simple. We already know the physics behind it. We know the engineering behind it. It's just that we need to make a concerted effort to dedicate ourselves to getting the job done. Yes, it will be expensive, but you have to ask yourself what the cost is of having no water whatsoever. When I was traveling in Cameroon, I was amazed at how the people in the area would use any container they could find, old plastic drink bottles, milk jugs, anything at all that had a cap, and they would go to the only source of water they could find, which generally looked like weak tea, a brown-colored liquid. And this is the water that they would manually haul home for washing and cooking. This is unacceptable. There's more than enough clean water in the world. Why don't they have water? In many cases, governments have taken the funds, or companies have taken the funds, and put them in other places rather than where they should be, getting that water clean. And while there's no money available for clean water, there's always millions of dollars for vaccinations and new government buildings. It makes you really wonder what's going on behind the scenes. But the same flat solar water heating panels that you see on many rooftops are actually quite capable of generating clean water. You see, the heat from them can be used to create steam or to sterilize water very easily, and variations of a theme work as well. Something as simple as a flat panel filled with dark pebbles and painted black on the inside can easily have water flowing through it and heat it to steam-like temperatures. It wouldn't take a lot of creativity to make large flat panels on the rooftops of buildings that not only would create clean water, but would keep a lot of the heat from getting inside and lower the load of air conditioning that's needed. In other words, we've already created the area to put a lot of this infrastructure for cleaning water and generating power. You see, all we have to do at this point is make it happen. We don't need to mandate it. We simply need to make it so easy and so accessible that everybody will do it as the default position. Once we've done that, we automatically will be creating clean water and power without adding any extra things to our environment that can damage it. And we don't need a law or a mandate to make it happen. We simply need to make such a compelling and simple case that everybody will want to do it. Coming up after the break on Talk Universe, we'll take some listener questions. We'll also have our Singularity Watch and my book recommendations as well. So now we get down to the listener questions, and we have a number of fascinating ones about water and water technology. Jason33 writes, is it true that they recycle the water, all of the water, on the International Space Station? That's a great question, and yes, it's true. They actually recycle wastewater from urine as well and turn it back into clean drinking water. Now, it's not as simple as just boiling it and filtering it. Their system has to be 100% recycling and nothing left over, so they have to take some extra steps. There are some molecules that boil off at a lower temperature than water. They tend to persist when you distill it, so you have to do extra steps to get rid of it. And take note of the fact that on most spacecraft, they use hydrogen fuel cells, and hydrogen and oxygen are the materials that go in to operate those fuel cells. And so when you run a fuel cell of any capacity, you end up with hot water as a result. And a lot of this is used for cooking. They have freeze-dried meals in pouches, and they inject this hot water from the fuel cells, which is pure water, directly into the food to cook it. So, and as a side note, anybody who uses a hydrogen-powered vehicle knows that if you're burning just hydrogen, you get nothing but water vapor out of the tailpipe. Now, this isn't 100% true if you're running at a very hot temperature in your engine. It will also tend to burn some nitrates, and you'll get some nitrogen oxides in the exhaust as well. So you have to be careful about the air mixture on a hydrogen engine. Emily M. from Peoria writes in, if all this water is inside the Earth, how does it get to the oceans? Actually, that's very simple, Emily. What happens is volcanic eruptions produce a huge amount of steam in the process. If you look at the plumes of smoke coming out of volcanoes, actually it isn't smoke. Most of it is steam. From 70 to 90% on average of the material ejected by volcanoes is water vapor or steam. So that's how all of it gets into our environment. Now, there's a lot of it that comes from underground artesian wells and flows from the water tables, but most of it comes from volcanic action. Here's an interesting one. Kagome 2002 writes, I've seen a lot of news about engines that burn water. How does this work? Well, the fact is, water is already the ash from burning hydrogen. There isn't energy to be had from burning water because water is already the end product. Now, you may be able to do some things like take some energy and split the water into hydrogen and oxygen and then burn that, but you're not going to get as much energy back as you started with. Now, water can certainly be used to accelerate or enhance how some fuels work, and adding some water to, for instance, a jet engine, it doesn't increase the fuel value of the jet fuel, but what it does is the water explodes into steam and produces a lot of pressure in the exhaust, so it actually can produce thrust, but it's a cost of energy that's involved in it. The water itself isn't a primary fuel, no. Now, some people may remember many years ago there was a scam going around where you were told that you could run on water in your gas tank by adding these pills or these tablets to the water. And what they were doing was, yes, they were putting water in the gas tank, but the tablets or the pills that you put in were made of calcium carbide. And what it would do is it would react with the water and produce acetylene gas. So you were actually having a chemical reaction occur in the tank that made acetylene, and that's what you were burning in your engine. And yeah, it would run for a while, but acetylene is extremely energetic, and eventually you would damage your engine. And then you'd have a tank full of water full of the leftovers from making acetylene. So it really was something that would destroy your car. Sure, it was a scam, and it would run for a while, but it would wreck your engine. Lucas G. from New York writes, I've seen the plans by Elon Musk to colonize Mars, and a lot of people are talking about going there. Is water on Mars the same as the water on the Earth? Absolutely. You know, it's just water molecules, and even if it's contaminated with something, you can distill it or filter it, and it'll be perfectly drinkable. So you wouldn't have any issues there. In fact, is a lot of water in space, and many of the moons of the larger planets like Jupiter and Saturn have huge shells of water ice and internal liquid oceans of water as well. Right now, they're looking at the moon of Saturn, Enceladus, because it's spouting water jets that contain organic molecules. They're going to be investigating that very shortly. And any of you who are interested, remember you can always email us your questions at admin@talkuniverse.org, or you can send them to our Facebook page, talkuniverse.org. So you can send questions at any time, and we'll take them on the air and answer them for you. Here's an interesting one from Arizona Anna. Does water actually have a memory like some people have said? Well, the humorous answer is, if it did, then you know the computer people would be all over it as a memory storage device. But actually, no, there's no evidence that there is. There are a lot of mystical sites that promote that idea and pseudoscience sites that do. But think about this. Let's say you had a big bag of Legos and you put them in the bag in a certain order, and then you poured them around and you stirred it all up, and then you went back to the bag. Would the Legos be in the same order? No, they wouldn't. And water molecules are freely moving, so there's nothing to hold any structure or organization in there. So if you stir them up or move them around in any way, any pattern that might have existed is completely destroyed or randomized. So no, water doesn't really have a memory. Now, Charlie from Boston asks, why does ice expand when it freezes? That's actually a good question. Water molecules are shaped kind of like a Mickey Mouse head. There's a big oxygen atom and two little hydrogens stuck on like ears. And when they're moving around freely, they can move in any position. They can be anywhere. But when they freeze, they only fit together in a specific crystal pattern. Imagine a set of shelves made of metal rods. When you put the shelves together, the rods join at the ends, and they come up with a large structure. But when you take them apart, all the rods will fit in a box, which is a much smaller space. So when water freezes, it's kind of like putting the shelves together. It'll only fit in one specific organization. So it's a larger organization. It occupies more space than if it were a liquid, like all the rods going back in the box. So that's why it expands when it freezes. It's the way the molecules stick together. Tanner51 from San Francisco says, we are having a terrible drought in California and have been for many months. What can be done about that? Well, the answer is you really have to have more water retention. You have to have cisterns and reservoirs set aside so that when the water is available, you'll be able to use it throughout the rest of the year when it's drier. The issue is, California is basically a desert in most of its area. Now, there are some more, wooded areas where there's a little more groundwater and a little more rain, but and along the coast, it's generally not too bad. However, in most of California, because there are barrier mountains, there's not a lot of rainfall on the interior, so you're really at the mercy of the water table and the water brought in by pipeline and whatever rain that falls. The real answer for the time being, of course, is better reservoirs. Many people can put underground reservoirs on their property so that rainfall comes, it actually goes into the tanks underground and then can be used later to water their lawns or their vegetables if they have gardens. And that's generally an unobtrusive, hidden way of doing it, and it doesn't get in the way of anything. And the water that you put in there can last for many months if you're very careful with it. In the future, obviously, there are things that we could do to increase the humidity and the rainfall in the area, and one of them would be the towers I mentioned that spray the water into the air offshore and take advantage of the breezes coming in off the coast. This would raise the humidity levels and hopefully some of the rainfall levels. But that's a big project and something that would cost billions of dollars, but it would have a very positive impact if it were done. Now, our Singularity Watch has an interesting feature here. An artificial spinal cord wirelessly restores walking in paralyzed monkeys. This is something that's really big stuff. There is a researcher by the name of Dr. Andrew Jackson, who's a neuroscientist at the Newcastle University in the UK. And what he's done is pioneer a project that puts a wireless neural prosthetic into the spinal cord of a paralyzed monkey. And the team was led by Dr. Gregoire Courtine at the Swiss Federal Institute of Technology. They've implanted a device that reads the signals directly out of the brain of the monkey and allows it to regain the control of its paralyzed limbs in just 6 days after the injury without any training required. This doesn't require any exoskeletons or external stimulations of the leg muscles in the patient, so it means that it can be used by patients in their own homes without doctor supervision. This is a sort of a brain-spine interface that uses an amazing technology, wirelessly getting the signals from the brain down to the muscle tissue by connecting directly to the nerves that have been damaged or severed. One of the things that's very important about this is that in this sort of an injury, a lot of times stem cells will not work properly. There are issues with the damaged tissue that don't allow the stem cells to work in a manner that would allow healing the way we would like. So this is a device that could allow you to regain control of paralyzed limbs very easily, or to add interfaces to external limbs such as arms, legs, or anything. Here's one everybody will like. University of Central Florida researchers have created a battery breakthrough that can charge in a matter of seconds, and the charge can last for a week. The design consists of a new type of capacitor that could replace lithium-ion batteries. Basically, it's a flexible material made of tungsten disulfide, and what it has is billions and billions of tiny conductive nanowires that are coated with a two-dimensional capacitor material. The coating on the material, the shell, is where the charge is stored. The new battery is extremely lightweight, it's flexible, and can be charged over 30,000 times without degradation. The overall design is actually a combination of tungsten trioxide and tungsten disulfide. This work is expected to create flexible, lightweight batteries that can be used in cell phones, electric vehicles, and just about everything else. This work was published recently in the journal ACS Nano. Also, I want to welcome our new listeners from Latvia, Moldova, and Puerto Rico. We have many new listeners on the site. We're glad you're here, and we want your feedback and your comments, so please send those to us. My book recommendation for this week is Water Wars, Privatization, Pollution, and Profit by Vandana Shiva. This is available in both paperback and hardback, and it's a book all about water. It's everything to do with the science and the society of historical erosion of community water rights, or communal water rights. And it looks at international trade law, how dams are created and the laws about that, and mining and aqua farming. And she's looking at how people are being disenfranchised from their rights to water. And it also looks at how economics and industry plays a part in that. A lot of times it's hidden under ethnic or religious wars. And this is really all about our right to have water. And when somebody says that nobody has a human right to water, it's the same as saying you have no right to sunlight or oxygen or dirt to stand on. And it's a ridiculous position. We all need water to live, and if you deny people water, you deny them life. This is very much about the common heritage of any living organism. You can imagine if you lived in a space station where everybody had to create everything you needed, such as oxygen and water and food. These were not things that you could simply have for free. I mean, we take oxygen for granted on the Earth. If you had to make the oxygen, would you have an oxygen bill every month? What a lot of companies and governments are doing is they're trying to act as if they own the resources of water, wind, sunlight, and oxygen. And this is not true. They are not ownable things. They were generated by the planet, created by the planet, and maintained by the planet, and we cannot own them. If you created your own world and you were creating those things, then yes, people who lived in that world would have some sort of an obligation to you, perhaps. But on the Earth, that's not true. We're not the owners. We are simply people who live here. We are stewards and proprietors, perhaps, but we don't have ownership. Now, it is up to us to make sure that we don't destroy the resources we have. This is what this is all about. If somebody moves in and begins destroying a resource, and it's something that we all need, a common item, such as the air or the water, then we have a responsibility to stop them and protect that resource. This isn't something they own. They have no right to claim it or destroy it. They certainly have no right to destroy what we need. And we're certainly not destroying it. We're simply living organisms doing what living organisms do. So when somebody claims to own the water or have the rights to the water and you don't have rights to water, in effect what they're saying is they're making a very bold claim that they have the right to decide whether you live or die and you don't. This is absolutely false. Nobody has that right. Nobody has the right to deprive you of life, liberty, and the pursuit of happiness. That's very clear. And maybe it would be helpful if you considered this in the context of creating your own world. If you did, what would you owe anybody else? Would you own every resource there if you had to create everything yourself? Think about the implications of that. For a world that nobody here created, who can claim ownership of something that they didn't create and they don't control? That makes no sense at all. Now let's step back and take the larger view. The world is a closed, finite system. It has limited resources. And we've grown to the point where we are challenging the limits of those resources. We have to do something in order to make it possible for us all to survive. Many people feel there's a plot to knock off most of the population, lower the population of the world. The real answer is managing our resources properly and learning how to clean what we've dirtied and create anew what we're missing. Consider, though, that no matter how much technology we have, no matter how much we learn how to do, unless our morality is in place and our ethics are workable, none of it's going to make a difference in the end. And remember the statement of Edwina Bach, "Make you the world a better or more beautiful place for having lived within it." For me, it's hard to think of a better and more noble sentiment. Thank you for listening to Talk Universe. I'm Sir Charles Schultz. Please join us again for another show. Good night.